Hello and welcome to the course From Data to Decisions. I'm Chris Mack, your instructor. This is Lecture 34, where we're going to look at the implications of having the wrong model when doing a regression. Recall that our assumptions in ordinary least squares regression involved a number of things, one of which was that the residuals of the fit are random. That is, there is no systematic component left in the residuals. The residuals do not depend on x. And another way of saying that is that we have the right model. We have the right equation to use. If we think about process modeling in its most general form, we're doing three things in this process modeling. First, we're finding the right equation to use, the right model form. That means two things: picking the right regressors, getting the right x variables that we're going to use, and second, the right form. That is, should it be x or log x or e to the x or x squared or what? That's the form of the model. So getting the right regressors, variables that control the output, and then having those regressors in the right model form. That's picking the right equation. Once we've got an equation, we can fit the equation to the data and extract our best estimates of the model coefficients, the parameters, the betas in this model. That's the next thing. That's generally what we think of as regression. And then the third thing is to characterize the nature of residuals epsilon. What is the probability distribution? What is the scale parameter? How much spread is there in these errors? Those are the three tasks. And these three tasks are all interrelated. We first pick an equation, we fit it to the model to get our best fit beta coefficients, then we look at what's left over and analyze the residuals and understand them. If anything changes, then all of these things change. In particular, if we have the wrong equation, then it affects the values of the coefficients and our understanding of residuals as well. So what happens if we have the wrong equation? Well, first of all, this error goes by a couple of different names. Model misspecification is one of them. Equation error is another, and you'll see these terms used quite frequently in different contexts. But picking the wrong equation means that there's something about variation in the response that isn't properly being explained. We can think of the process modeling as dividing up all the variation in y into two piles. One pile is the systematic variation, which we try to explain with our model, and the other is the random variation, which is the leftover piece that falls into epsilon residuals. There are two things that can go wrong if we pick the wrong equation. One is, and the most common is, underfitting. That is, we don't have all the right regressor variables in our model, and we don't have the right model form, and therefore there's some systematic variation in y that is left unexplained. We have some systematic differences between the data and the model that are being lumped into the residuals, and our residuals are not just purely random. We call this underfitting. Overfitting, on the other hand, is less common, but can in fact happen, and does in fact happen. This is where I have too many model parameters, too many regressive variables, or too many forms of the given regressor variables, such that our model is fitting the noise. We have some random variation in y that's being lumped in to what the model is trying to predict. We're just assuming this random variation is in fact systematic. This gives a better fit, but less predictive power to our model. Overall, we're going to try to use some measures of the goodness of fit to help us understand whether we're overfitting, underfitting, or doing things quite well. And this will be our first lecture talking about some measures of goodness of fit, and in coming lectures we'll see more. the first way to get at the problem of whether or not we've got the right equation, whether or not we're fitting with our model all the systematic variation in the data, the first defense is graphing. Here's a graph from that famous paper that I've referred to a number of times by Francis Hanscom, Graphs in Statistical Analysis, where we've got a best fit line to a set of data that obviously has a second order curvature to it. So there's some systematic variation that's not being captured by our model. So graphing is the easiest way to detect at least gross variations, differences between the model and the systematic behavior in our data. But you have to be a little bit careful because we've got two kinds of variation in Y. One is the systematic variation and one is the random variation. And sometimes the systematic variation is so large that the random variation might be hidden. And you won't notice it in a graph of response versus regressor. So here's a graph of some data. This is from a NIST study website. And we've got the Y variable versus the X variable. And we fit it with a straight line model. And boy, that looks like a good fit to me. Right? The line goes right through the data points. Everything looks pretty nice. So if I were to just look at this fit of how the model matches the data, I might assume that we don't have any problem with equation error. We've got the right model. But when I, in fact, plot the residuals, I see a different story. Here, residuals show a systematic variation in behavior as a function of X. There's a very small second order term. Very small second order term that is not being captured by captured by a linear model, and we can't see it except for by plotting the residuals. So plotting the residuals is the most important way in which we can understand visually whether or not we have any equation error. That said, is a word of caution. The human brain is geared towards pattern recognition. Our brains can pick out patterns from randomness very, very easily. In fact, it often picks out patterns from randomness when there is no pattern. We make up patterns. This happens all the time, and especially if you don't have very many data points. So here's an example of a residual plot versus the X variable. And if you were to just look at that with your eyes, I think almost all of us would pick out this curved behavior, second order behavior, and say, oh, it looks like we need a second order term in our model to capture that. But do we really? Is this really what's going on? And there's not that many data points. And if there's a reasonable amount of spread in the data, maybe just randomly got a couple of low points at the beginning and at the end as a function of the X variable. And then, in fact, this happened just because of random chance. Maybe we've got heteroscedasticity, not model error. Maybe we've got just some random variation going on. So graphing is really good, especially if you have a lot of data points, but it's not the perfect solution to understanding model error. Only the first defense. What else can we do besides graphing? Well, one thing we can do is something called chi-square testing. When we do a least squares regression, what we're trying to do is minimize the sum of the squares of the residuals. And in particular, if we have a weighting or an uncertainty in each of the I data points, we'll call that sigma sub I, the standard deviation of the measurement error for each measured I response variable. What we're trying to minimize is this sum of weighted values called chi-square. If the OLS assumptions are true, then these residuals will be normally distributed. If these are normally distributed, then a sum of normally distributed variables that are squared turns out to be a distribution called a chi-square distribution. Well, it's not a coincidence that we gave this variable name chi-squared, because for the normal assumptions, it is in fact chi-squared distributed. The number of degrees of freedom is n minus p, where n is the number of data points and p is the number of parameters in the model. If the assumptions of OLS are true, that is, we do have independent normally distributed residuals, then we can test the assumption that this in fact is chi-square distributed. Just to give you a little idea of what the chi-square distribution looks like, here are some graphs of the chi-square distribution for a few different values of the degrees of freedom, n minus p. The expectation value for chi-square will equal the number of degrees of freedom. The variance of chi-square will be twice the number of degrees of freedom. So how do we test equation error using this statistic chi-square? Well, first of all, in order to calculate chi-square, we must have some knowledge of what the sigma I are. Remember, the sigma I are the measurement errors in each individual I response, I Y value. We cannot arrive at this information from the data. The data does not tell us what the sigma I are. We need to calculate what the sigma I are through some independent measure. So a priori, we know something about our measurement technique. We know something about our samples, and we have an understanding that if we make measurements, we get a certain level of uncertainty in those measurements, sigma I. We have to know that ahead of time. But let's assume we do. Let's assume we have that knowledge, we have that information ahead of time. Then we can calculate what chi-square is for our data set. So we've done our best fit. We have the sum of the squares of the residuals weighted by sigma I. That's our chi-square for the data. We can ask, what is the probability of getting that specific chi-square value, or something more extreme than that, given just random error? Now, assuming a chi-square distribution means we're assuming normal homoscedastic residuals, and this statistic is very sensitive to that assumption. If we don't have normal residuals, if we don't have homoscedastic residuals, we will get a value for chi-square that's way off from what we would expect otherwise. So we have to check the assumptions of normal distribution and homoscedastic residuals first before we could possibly do a chi-square test. And only after we're convinced we have normal residuals and homoscedastic residuals should we even attempt to do a chi-square test. But if we do, then we can calculate the p-value for and compare it to our significance level, alpha. So 0.05, 0.01 value for alpha. We can calculate the p-value, the probability of getting a chi-square statistic this extreme or greater, given the assumptions. And then ask, can we reject null hypothesis that the model accounts for all the variation in Y except measurement error? That's the test that we will perform. One way of looking at chi-square goodness of fit test is by calculating the reduced chi-square. The reduced chi-square is simply the chi-square divided by the degrees of freedom. Why do we do that? Well, because the expectation value of chi-square is the number of degrees of freedom. Therefore, the expected value of the reduced chi-square is 1. And we can start looking at magnitude of this reduced chi-square for any number of degrees of freedom and ask, how does it compare to 1? If the reduced value of chi-square is much, much bigger than 1, then our model is not accounting for all the variance in Y. There is variance in Y that is not being explained by the model. There's something missing from the model. But there's another possibility. Our estimate of the measurement error is too low. We assume a really small measurement error, and in fact our measurements had a lot more uncertainty in them. We could also get the reduced chi-square much, much bigger than 1. So one of those two things is true. if the reduced chi-square is much bigger than 1. Either we don't have the right model, we have missing regressors, or we have the wrong model form. In other words, we have equation error, or we've done a bad job of estimating the error variance. That estimate is too low. On the other hand, if the reduced chi-square is much less than 1, then we're fitting the noise. We have a model with too many degrees, too many parameters, and we're able to fit the noise. Another possibility, though, is that our error variance estimate is too high, that we assumed we had this large uncertainty in making measurements, and in fact our measurements are much, much better than that. And that could also be the cause. So we still have two possibilities when the reduced chi-square is much, much less than 1. If the reduced chi-square is about equal to 1, then we say we've got a good model fit. That is, variance in y is explained in a very good way by a model plus a measurement error. That's, of course, the desired situation, what we hope for when we do our fits. Let's look at a simple case. A very common case is where we assume the uncertainty in each measured value is a constant. So sigma I just becomes sigma, the measurement error, for each y value. In that case, I can take the reduced chi-square, which is this formula, take the sigma I squared and pull it out, summation, put it out in front. And then I notice that this summation of the residual squared divided by the degrees of freedom is nothing more than the standard error of the residual squared. So in fact, the reduced chi-square is the standard error of the residuals from our best fit model divided by our measurement uncertainty estimate squared. Well, we can do a chi-square test on this, and here are in fact some critical values of the reduced chi-square as a function of the degrees of freedom. And you can see this critical value approaches 1 as the degrees of freedom goes to infinity. Here I show a couple of significance levels, 0.01 or 0.05. You kind of get some basic rules of thumb, especially if you have, say, 20 or more data points, 20 or more degrees of freedom, and you're typically looking at values in the 1.5 or 2 range and below. See a reduced chi-square, this thing, less than about 1.5 or maybe less than about 2, something like that, and you're probably in the ballpark of a good model with no detectable equation error. Start seeing reduced chi-square values above 1.5 or above 2. Certainly if you see things that are 4 or 5 or 6, that's a good indication that you do have equation error. An alternate view is to ask the question, what amount of measurement error would allow me to pass this test? So I look at the critical value for a certain number of data points and then say, all right, given a certain variance of the residuals, standard error of the residual squared, what measurement error would allow me to pass the test? And is that reasonable? Would that be possibly the true value of the amount of measurement error? If it doesn't seem reasonable, again, that's an indication that you really do have equation error, the wrong model. Of course, we can do the same thing for a weighted regression if we use our usual weights. Our usual weights are weights equal to 1 over the measurement error squared for each data point I. If we use those weights, then our standard error of the weighted residual squared is the same thing as the reduced chi-square. Well, that just means we can take the standard error of the weighted residuals and compare it to 1. Or the standard error of the weighted residual squared compared to 1. And do our chi-square test in the same way as always. That's, of course, assuming that we've used the usual weights. If we use some different weighting, then this doesn't work. And finally, chi-square for a total regression, same thing. In a total regression, we are summing up the errors in the y variables plus the errors in the x variables as well, squaring them and weighting them by 1 over the uncertainty in the y measurement and the uncertainty in the x measurement. So if we use this sum of squared errors, then this sum S will also be chi-squared distributed with n minus p degrees of freedom, where p in this case is the number of model parameters excluding the n predicted x values. So we don't think of these x hats as parameters in this chi-square distribution. So again, we can do a reduced chi-square, compare it to 1, just like before. So what have we learned in Lecture 34? As always, you should be able to quickly and easily answer these questions. How can we use graphing to detect equation error? What is required if we want to perform a chi-square fit of the residuals in order to find equation error? That is a chi-square goodness of fit test. What is the reduced chi-square and what is its expected value? And finally, what are the assumptions that go into this chi-square test? Well, in the next lecture, we'll look at a couple of other measures of goodness of fit. Again, test for having a good model based on those. Till then.